12 minutes from now. Yeah. Hello. Good afternoon. I welcome you all for my PhD-Defense. And when I look around in the room, I see many fluid dynamicists sitting among us. And I hope that you all share my love for fluid dynamics. And I hope to keep you entertained for the next 1 hour or so. And to give you some examples of why I know that most of us love fluid dynamics, here is an evidence. So this is one of my paronyms, Utkarsh. And we had just realized that cloud is nothing but a collection of droplets. And that's why he looks so amused here with the sunglasses on. But OK, that's not the only picture. We also have him here drinking tea and pointing at the clouds. So that's great. It was a bit difficult for the second paronym because he's a bit camera shy. But I could find one picture with the background with some fluid flow going on. So with that, I thank both Utkarsh and Udalok to be here. Thanks a lot. You can now have your seats. So today I'm going to hope to keep you entertained with my thesis. OK, before that, sorry. So there's some housekeeping. So there was an article, a comic in 1919, when the pocket telephone rang. Actually, this is a time when the pocket telephone, or mobile as we call them, was not invented yet. And so this person got it quite right. So I ask you all to please turn off your phone or keep it in silent so that it doesn't ring in between. OK, so with that housekeeping out of the way, so today I'm going to defend my thesis, which is titled Viscous Free Surface Flows. And as an evidence, we see a droplet wearing a crown, which is the POF logo on the slide. So I will just give you, I can split this title into two parts. One is a free surface flow. So what is a free surface flow? It's essentially any fluid flow in two phases, where one of the phase offer negligible viscous resistance to the flow. So for example, you can see this very nice lake where this flow is going on, and then outside it's air, so it's a free surface there. Another example would be when you fill a glass of water like this from a tap. And this was incidentally my first research project when I was an undergrad about 8 years ago. And this is what happens inside the glass. So you see all this bubble cluster. And I'm sure that you all have seen this picture many times, because this is one of my favorite pictures. And as a proof that I also did experiments at some point of my life. Moving on, the second part, which is the viscous, which has a term viscous. So for that example, you can look at honey, for example, where you can see this very nice thick thread coming down. And so essentially what I will try to do in this thesis is I will try to look at free surface flows and study the effect of viscous dissipation on these free surface flows. So that's in a nutshell the thesis. So that's the cover. So now I'm just going to, I will just explain the different things that you see on the cover. So part one of my thesis is on drop impact, which is the photo right there. And for that, I show you a video which is taken at the International Space Station. This is Scott Kelly who took this video, and he's playing ping pong with a water droplet. So that's this video. And of course, both pedals that you see, they are super hydrophobic. So they don't like water, so they repel water. And so that he can play ping pong with a water droplet. So which brings me to the part one, and then once you look at this video, you can ask several questions that might invoke your curiosity. So the ones that invoked my curiosity was, how much force does Scott have to apply on these paddles to keep it stationary, right? Because you are playing ping pong, so in order to keep it stationary, how much force you need to apply? And that question I answer in chapter 1 of my thesis. So that's the first chapter. The second, of course, is you see this droplet bouncing up and down. So it will keep on happening like this for a while. So the question is, how long or when will this drop stop bouncing? Because at some point, you can imagine that viscous dissipation will kick in, and it will stop this drop from bouncing, and then this drop will stop. And that's chapter 2 of my thesis. That's precisely that will try to answer when will this drop stop bouncing. Moving on, since we should also, as scientists, we should also think about like applications or industries at times. And what happens in an inkjet printing for industry, for example, you never get a dry substrate. So you always have a coating on the substrate. For example, your paper, you first coat it with a primer, and then you would impinge droplets on it. So the next question was, what happens if I coat this paddle with a viscous liquid, and then what would happen to these this phenomenon? That's chapter 3 of my thesis. And lastly, chapter 4 is if I have a droplet already on the paddle and I throw another droplet on top of it, then what happens? So it's a two-body problem with two droplets interacting with each other. And that's chapter 4 of my thesis. And with that, so that's the first part of the cover. The second is this jet, and that's the part 2, which is retraction and bursting. And for that, you can look at this video. So this is a soap bubble, like a soap bubble, which pinches at the bottom, and then it bursts because of surface tension. And this retraction is what we study. But what we study here is how does the surrounding, for example, in this case air, but it can also be a different liquid in the surrounding, how does that surrounding influence this bursting process? So that's the 5th chapter of my thesis. And lastly, since we can, if everything goes well, we can celebrate, and that's essentially a glass of champagne here. And you can see below the glass of champagne, we have a bubble here, which does something like that. And on the top, you see these jets coming out, and these droplets breaking into this jet breaking into droplets. And if you ever put your hand on top of a glass of champagne, you will always feel wet because of these droplets. So that's another let's say thing that interested me a lot. In fact, one of our audience members, Javi, has also worked on this exact problem. And of course, what is also interesting is when you look at mud pots. So this is a mud pot in the Yellowstone National Park. You see these bubbles which come to the surface and they pop, and they show very similar features. So my question was, can we use the things that we learned from a glass of champagne and apply this to these kind of situations and understand this process? And that's chapter 6 of my thesis, which is how does viscosity and viscoplasticity. So these liquids are special because it's a mud. It's not just not just a viscous liquid. So how does viscosity and viscoplasticity influence this bursting process? So that's chapter 6 of my thesis. So with that, I would like to thank you for your attention, and you can scan this QR code to get my thesis. Also, I believe in openness in science, and I believe in openly sharing things, and also in the reproducibility of data. And as a result, all the codes that I have used in this thesis are all publicly available online with no license required. So you could always visit at my sandbox or my GitHub, and you can always download these codes to reproduce. With that, thanks a lot, and I hope to keep you entertained.
I open this public meeting of the Doctorate Board of the University of Twente. I would like to express my welcome to all of you, in particular to the candidate and his family and the members of the committee and the paranims, the members of the committee, and so especially I want to welcome the people that are joining us from online, which are Professor Quéré from ESPCI and LADIX in Paris, Professor Rolfs from the University of Twente, and the promoter, Professor Detlef Loze, and here in the audience are Professor Van Brummelen from the Technical University of Eindhoven, Dr. Jalal from the University of Amsterdam, and Professor van der Linde from the University of Twente. So Dear candidate, could the candidate and his paronyms come forward, please? Dear candidate, are you ready for your defense?
Yes.
Then I would like to ask the first opponent, Professor Quéré, to start the opposition.
So I'm very happy to be part of this committee. Of course, I deeply regret not to be here in person. I really enjoyed to read your PhD thesis. It's very rich. It's brilliant. I like the style. I like the fact that we see a mixture of experiments, numerics, and theoretical arguments. If we say something very general, we could say that generally a PhD, you dig something very deep, or you touch many subfields, and it's your case. I think it's more risky because there is the risk to be superficial, but it's not the feeling we have. All the kind of papers that you collected are all interesting, all well written, comprehensive, and so they generate many natural questions. And I think it's a very good sign. When we have many questions, it means that there is something which remains open to the discussion, which is the reason why we are here today. In my particular case, I would say that you touch many things that I have been interested in, so I maybe have even more questions. However, we have time restrictions, and I will mix general questions and detailed ones. So I start by the chapter 1, and I have a general question about it, which is about the role of air in this in the analysis. What about the water hammer model, for instance? What about the Leidenfrost case, which are two cases where air, either theoretically or practically, should play a role?
Dear highly learned opponent, first of all, thanks a lot for your kind words on my thesis, and thanks a lot for your question. And coming to your general question about chapter 1, so indeed air layer would play a role. In fact, if you look at the previous works from Leonardo Gordios and group, they did these experiments on a hydrophilic substrate, and so then you don't get the second peak, you only get the first peak, and they have some reasons of what that peak should be. That comes from the modified Wagner theory. And what we do the experiments on a super hydrophobic substrate and do the numerics with a thin air layer. And what we see is that the first peak is exactly the same as the ones that was predicted by the modified Wagner theory, where you don't account for the air layer. So what I would say is that for the first peak, the first drop impact peak, it doesn't matter, like whether you have a air layer. For example, in Leidenfrost, because my system, if we forget about phase change for a minute, my system, the numerical system would mimic a Leidenfrost system much better than, let's say, the one on a super hydrophobic substrate, because you have a air layer, as you mentioned. That's quite right. For water hammer, I'm a bit shaky because I exactly don't know what the equation is. But if I have to venture a guess, I would say that the first peak will still remain the same. Regarding the second peak, as we see that even our results agree quite well with the experimental results on a super hydrophobic substrate. So I don't see a reason why it should not also explain things about Leidenfrost or water hammer. But for Leidenfrost, I am sure. But for the water hammer, I will have to look it up.
When you say you are sure, you mean you did something about that, or?
I did not. So it's something that we talked with one of your PhD students, Pierre Chantelo. Well, he's now a postdoc in our group, and he does this Leidenfrost drop impact problems. And it's possible that we might think of experimentally verifying what I've just said. But numerically, since my system assumes an air layer, well, of course, in Leidenfrost it's a vapor plus air layer and not just an air layer. but mechanistically, since what we also see is that the microscopic features of that air layer doesn't really matter a lot. What matters is that there should be an air layer. Because, for example, in my numerical simulations, I cannot say anything of the length scales which are smaller than 1 micron. So smaller than 3 orders of magnitude, smaller than the drop radius, which in our case is 1 micron. So we cannot really say anything about the flow features below that scale, because that's below our grid scale. And so what really matters is that that air layer or that cushion is present, and rather not like what it does. So and that's the case for Leidenfrost as well. So if I have to speculate right now, I would say that it should be the same. But of course, we would need an experimental verification, which well, you might see in a few months if everything goes well. Yeah.
I have also a detailed question about this chapter. If you go to page 40, okay, you have this sequence of pictures. In all cases, we see, in a sense, 2 Worthington jets. We see one at TM and we see one at T2, okay? And so, according to your arguments, we should see 2 peaks in force. So the secondary peak should be double in a sense.
So so first of all, the first like at T equals to Tm, the Worthington jet that you are seeing, it's not really a Worthington jet in the real sense, because because it's still coming.
Like
it's like, yes. And if you look in the on previous page, on page 39. So there in figure A on page 39, I mark this Tm, and you do see those wiggles. So this actually is again can be explained from one of your papers on pyramidal drops, because it's not just that peak, because it's all like a capillary waves which are coming in from the sides, and these oscillations that you see between, let's say, Tm and T2, all those oscillations are because of those waves, including this Worthington-like jet that you just mentioned at TM. So it's in line with the pyramidal drop impact paper that you worked on in JFM.
I see. Oh, yeah, good remark. Yeah. So about the chapter 2, so you discuss the possibility to stop the bouncing by the weight or by the viscosity. It's a funny thing, because you treat bouncing as if it were a normal phenomenon, and it's a very exceptional phenomenon. And it has mainly to do with the wetting conditions, the fact that you are in a non-wetting situation. There is very little in the literature about the transition between bouncing and non-bouncing when you vary the contact angle. So it is said that around 150 degrees, suddenly you... So do you have something to say about that? So can you treat this transition of wetting with your arguments, or more concretely, for you, what is the main cause why you kill bouncing when you reduce even a little bit the contact angle?
Well, I would imagine that there will be multiple factors, as you mentioned, that we restrict ourselves to only the theoretical case where the contact angle is 180 degrees. But indeed, in real life, it's not the case. And in fact, there's a recent paper which I cite in the conclusion of that chapter, where people see non-bouncing even at Onizog number of 0.2, which we predict should be 1 if the bond number goes to 0. And the reason there is indeed because of the contact angle, because they do it or contact angles or even pinning effect. So there can be multiple things. One would be the pinning effect, that the contact line pins and then you won't be able to take off, or you would take off a part of the droplet and a part will remain on the substrate. What could also happen is that during retraction, the contact angle kind of drags, like something like a corner flow problem, and then they would have viscous dissipation, which we all know diverges as you go closer to the contact line. What I was looking for is something like a Taylor scraper flow when you have a contact angle which is like this and not really 180 degrees, and then that could lead to contact line dissipation, which would dominate, and that can also kill the kinetic energy. So there could be multiple reasons. I give you 2, but maybe. But I would suspect, especially in experiments, because this citation which I give, they say that they do it on a soot the superhydrophobic substrate made using soot, which should ideally be the same as the ones that Aditya, for example, from your group used. However, they still see non-bouncing at 0.2, which is still puzzling to me, that why would it be 0.2 instead of 0.8 as you have mentioned, or 1 that I say in the limit of zero bond. So it's still, I would say it's still an open question, and I do intend to look into that in the future, actually.
Professor Carré, can you be satisfied with this answer?
Yeah, I'm very satisfied with the answers. Thank you.
Thank you very much.
Thank you.
Then I would like to give the word to the next opponent, Professor Van Brummelen.
Dank u wel, meneer de rector. So before continuing the opposition, I would also like to congratulate you on your thesis. You provide a, in my opinion, comprehensive investigation of droplet impact and retraction and bursting of liquid films. And joining Professor Carré, I appreciate the difference in research techniques that you use. So it's experimental, theoretical, and numerical, which is very interesting. At the same time, your thesis is also well written. It has very nice illustrations, and I sincerely enjoyed reading it. I think actually my first question is also a bit related to this discussion that you just had, because what I was wondering about, or what I would expect, is actually that dynamic wetting conditions play an important role in the, especially in the droplet bouncing. Nonetheless, you do not discuss those very thoroughly. So my question is, how are wetting effects or dynamic wetting effects actually included in your model, and which role do they play?
Dear highly learned opponent, thanks a lot for your kind words on my thesis, and of course thanks a lot for the question. I was sort of expecting this question, I must say. So, well, when we think about dynamic wetting, it's essentially, we talk about a dynamic contact angle at the substrate, right? Like that contact angle that would change with the flow because of the velocity field and so on. However, theoretically, the static contact angle will always remain the same. And then you would, like the contact angle, which is the property of the liquid and the solid. So that would still be the same, but the dynamic contact angle will change. And if you look at any theory, like for example, Cox-Winoff or any of the dynamic contact angle, dynamic wetting models, all of them, they have this assumption that they have this thing that the static angle remains the same at the substrate. And if you look at, let's say, any of the figures in the thesis, for example, let's look at figure 1.2, and you can see that even though the static contact angle is 180 degrees, because I assume an air layer, so it has to be 180 degrees. So that's page 20. But you can see in figure 4, for example, like 1.2 and subset 4, that there is an apparent or a dynamic contact angle which changes as the flow happens. So there is a paper by one of the person who's sitting in the audience, Yusuf, who looked into the effect of contact angles and the different models. So he compared the generalized lubrication model from Yako, who's in our group, with the simulations of Basilisk and Jerris, and he indeed see the same. So as long as you are careful with the static contact angle being the same as the property, and you are careful with the refinement near the contact line, you don't need a dynamic contact angle model.
I would argue there's a second part to that, which is actually the slip that you have at the contact line.
Yes, that is true.
And actually, that sort of naturally takes me to my second question, which is simply a follow-up. Is that in, say, figure 242b, where you plot, say, dissipation in the droplet, there you would see something which you could call a dissipation hotspot near the contact line, which suggests actually that the dissipation is very sensitive to the slip model that you would use. Right? So it's not just the contact angle and the dynamic contact angle or static, but also the slip.
So indeed, what we did was we did not use a slip model, which means by default that our slip length is delta by 2, where delta is my grid size. That's again something that Yusuf proved conclusively in his Journal of Computational Physics paper. Probably that it was a JCP, but okay, anyway. So it's delta by 2, and what you see is that, okay, that slip length is there, but it's not something which I control. It's something that I can change, of course. So what I did do was I changed the grid level of resolution. So for example, most of my results, they have at least 1,000 grid cells around across the radius of the droplet, but I could change that to 500 or 2,000, but not to 10,000, I must say. And what I can compute is the viscous dissipation, and I try to look at the hotspots, do they change, and they don't. So even with a 500 grid cells across the radius, it still is the same result. So that's what I can say, that it's independent of the slip model.
So apparently that suggests that actually, so my starting point is I would expect that it is sensitive to that, and I guess your results indicate that it's not. It's not very sensitive to the slip that you have.
Yes, indeed, yes.
Okay. Another aspect which intrigued me is also is the role of the Ohnesorger number, and then in particular as it passes to 0, which I guess you would expect. That's right. You anticipated my first question. I guess you could also anticipate the second one. So in figure 244, you present the energy budgets for viscous droplets and then passing Ohnesorger to 0. And what you observe is that basically there remains dissipation in the limit as Ohnesorger goes to 0.
Yes.
That's of course completely counterintuitive.
Yes.
Well, my intuition failed me in the first question, so possibly it does in the second as well. But can you sort of rationalize for me why we still observe what happens in the limit as Ohnesorger goes to 0?
So a short answer to your question is that I cannot rationalize it right now, because it's something that I also thought of while looking at these graphs, and that what is happening here is that in the limit of 0 Ohnesorg number, or let's talk if we talk dimensionally, in the limit of 0 viscosity, we still see finite dissipation, which naively I would expect not to see, because if it's exactly 0, it's an inviscid flow, it should not dissipate energy. But then the other day what I was reading around and what I found is that it could be related to something called a classical anomaly, where the symmetry breaking parameter, which is viscosity in this case in the flow, even when it goes to 0, the effect, which is the dissipation in this case, doesn't go to 0. And that's not something which is, let's say, something new which I found out, because if you look at, let's say, for example, chapter 5, which is Taylor-Equilibric retractions, even there you see, even if we have a very small Ohnesorg number, it doesn't go exactly to 0. So it's still a finite, but but right now I won't be able to conclusively tell you why it's not. But it's probably related to this role of viscous dissipation, which is actually the main part of this topic of this thesis.
So
as well.
in my question, I will not force you to give a conclusive answer to that, but do you have a conjecture?
Yes, most likely what happens is that even in the limit of 0, let's say, because when I say 0 limit of viscosity, I don't mean exactly 0.
No,
right?
I mean so in passing to
passing to 0. There you could still have very high strain rates, right? And viscous dissipation is not just viscosity; it's viscosity times strain rate times some other things, which means that when I go to very small viscosities, I increase my strain rate, and which means that the product of those two, I mean, there is no, let's say, argument that unless that prefactor is 0, like the viscosity is 0 itself, there is no reason why it should be exactly 0 and why it should not be finite. So another question which might be intriguing is, why does it remain constant? Like, why doesn't it, like, taper down towards 0 or something like that? Why is it finite? And what we also see in, let's say, drop impact is that in that limit, after a while, you would see that even though viscous dissipation at takeoff, even if it goes to like a small value, the internal kinetic energy of the drop increases. So at the end, like the usable energy that the drop has is still goes to a finite value. Which can explain why we see a finite value of epsilon on the previous page, but it still doesn't explain why we see a finite value of dissipation. But that's my working hypothesis right now, that it has to do with strain rate not going to very high values when the viscosity goes to a small value.
Okay,
yes,
that seems plausible. Is there time for a very short?
A short question and a short answer.
It's a very practical one. So. What has been your experience with the time step in your numerical simulation methods? Because that's not something you discuss extensively. Yeah. So for all my, I'm speaking from experience. I keep my time steps smaller than the time period of oscillation of the strongest capillary wave. So the capillary wave with the smallest lambda in the simulation, which is the grid size. But it also suggests that if you do a mesh study, you need to decrease your time step as you refine. It does it automatically. Yeah, it does it. Okay. So there's a delta. So in the time step there is a delta cube. So it's not delta; it's delta cube to the square root, because it's a capillary time scale. Yeah. So refining the mesh is painful.
Very.
Yeah.
Yes.
Okay. Thank you. Yes.
Thank you. Then I would like to ask Dr. Jalal to continue the opposition.
Thanks so much, dear candidates. Let me also join the other opponent to congratulate you with the beautiful thesis. I much enjoyed reading all the chapters. The attention you pay and the care you have for the every single graph is exceptional, and I much enjoyed that, and also all the discussion and beautiful results. But I have also a couple of questions that I wanted to discuss with you. Let me follow up with some asymptotic limits from the previous opponent about in chapter 1. When you discussed the first peak in the force, and you propose a correlation function that is 0.81 plus another coefficients to the Weber to the -1. So the limit of high Weber number is very curious, but very well defined, coming from scaling law. But what happens when the Weber number goes to very small value? This, based on your correlation, it seems like the force blows up. Is that physical? Can you discuss a little bit?
Dear highly learned opponent, thanks a lot for your question and your kind words on the thesis. So indeed, yes, and you also actually asked me a question which I am a bit uncomfortable with, because I don't particularly enjoy writing that equation in the form where I just say, okay, we take it from dimension analysis and we just plug numbers, and then we have two basically fitting parameters that gives us that 1/Weber dependence. What happens at low Weber numbers is essentially that the capillary oscillations will dominate, so that the pressure inside the drop, because since let's say Weber 1 is means that the inertia and capillarity, they have the equal, like the same order of magnitude. Below Weber 1, it's capillarity which dominates over inertia, so which means that inside the drop you have a pressure which is driven by capillarity, and if you do those basically if you calculate the force by integrating the pressure on the substrate, then this should come out, like 1/Weber should come out, but that's something that we still need to check. Particularly because the let's say the spreading area is also, because we would do an integration of pressure over the spreading area, and for let's say high Weber numbers, we know how that area changes, because we know modified Wagner theory, we know the square root behavior in time, and so on and so forth, and so it's a bit easy to properly define the asymptote of the high Weber numbers. For low Weber numbers, it's still a work in progress. So, but the reason why it is 1/Weber, and we think it's true, is because the pressure inside the drop is capillary.
So if Weber number was orders of magnitude smaller than 1, you're expecting an infinite force on the...
Not really, because with the Weber number, which is quite small, you would also kill deformations of the drop, because then it would be like a solid ball impacting on a substrate. Of course, you have to also think about, because the drop will have a finite viscosity, whereas the substrate is rigid. So you're impacting something which is still which can still deform to something which has an infinite resistance to motion. So it will still give you some force, but probably we'll have to look into. But what happens in that limit? It's still an open question. Like what happens to much smaller Weber numbers? For example, Weber 0. Well, Weber 0, you expect a 0 force, right?
Indeed.
Yeah.
But that's not what the equation gives.
But that's not what the equation gives, indeed. And there has to be something that regularizes this thing towards small Weber. We don't know that yet.
So let me very quickly stay in the same section, and about the other correlation that you have, and that's the depending on the second force to Weber number to the power -1. And later you find this asymptotic limit again in the high Weber number when the force stays constant in your numerical simulations. I understand that in the experiment the splashing happens and you lose the second peak. But in your numerics, again, well explained, you get to this asymptotic because it's axisymmetric. But do you have any physical insight, and if it's not keep it short, it's fine, about this -1 asymptotic of dependency on Weber number for the second force, and then the value of 0.37?
So it's between basically like the peak, the singular peak, like in the singular regime, and that connecting to the inertial regime. That's the -1 you're talking about. Yes. It's basically a transition regime. And if you look at so essentially at some point I give a relation between force and the different flow parameter, which is like Vj, like the jet velocity, the retraction velocity, and d2. And this what this tells you is that force is essentially similar to Vj. And what we see, which has been seen before also in the literature, is that the Vj scales as 1/Weber. But we were unable to, from first principle, relate this Vj with the impact parameter, which is Weber, which is again.
And I assume that's also pretty much the same for the asymptotic of 0.37 That's just something that
it's
came
something
out
because
of
all
the-
three of them goes to a constant value. So and so that in the dimensionless space that I'm talking about. So
Indeed,
indeed
yeah.
they don't go to a constant value. The Vj scales as V and so V2 scales as V, and there's a scale with Vj and D2 as well. But
And it's a very short transition, so it's very also hard to
exactly. And also, for example, if you look at 1 over Weber, and we only have I don't think we have 1 decade even. So I would be very uncomfortable telling you for a fact that this has to be 1 over Weber, because it's just not.
Indeed,
It's just not there.
Okay.
It's
So-
a transition.
Perfect, acceptable. So let me do a little bit of more general question about when I was reading your chapter about forces, like you said, discussing in the discussion, I thought this can be very important when you design superhydrophobic surfaces, so they make them better potentially. Towards the end, you mentioned about micro scale of superhydrophobic surfaces. So you suggested, based on reference 49, that reducing the spacing of the texture can be something that one can do to make a better superhydrophobic surface. Your model, your numerical model, doesn't have anything to do with the micro scale, right? But the surfaces still stay superhydrophobic. Does it mean your numerical model is valid for a group of superhydrophobic surfaces only?
For that, I would first need to know that what group of superhydrophobic surfaces you mean, because for me, what a superhydrophobic surface is that the drop is on a cushion of air and not direct contact with the substrate. But of course, when you try to make it experimentally, you cannot exactly get to this limit. So you would put up pillars or do something so that you would have air pockets, so that the drop is most of the drop is on the air layer and not really on touching the substrate. So as long as that hypothesis is valid, so the more experimentalists would make their surfaces which can mimic a perfect superhydrophobic surfaces, the better my model will be able to let's say mimic the scenarios. However, what we do see again is that more often than not, it doesn't really matter how that air layer looks, but rather that air layer is present. And that's pretty much, and that's what was also one of the, let's say, key insights that I was able to gain from this while working on these problems.
Okay. For the sake of time, let me switch to chapter 6 and ask 1 or 2 questions if there was time.
Short question and possibly a short answer.
Okay.
Yeah.
So I have to choose now between my questions. So let me ask it. So I asked a very short one. So when you discuss your results of chapter 6, you have these beautiful plots of the second invariant of the stress tensor or the strain rate tensor. Why the second invariant? Why not the first invariant and other invariants of the tensor?
Well, it was just a choice because that's pretty much what goes inside the Bingham model that we use as well. And so what we wanted to get is that how do we define like something that is not yielded yet. And for us, that was more intuitive to use a second invariant. However, if you go to, let's say, more exotic fluids, then maybe it would make sense to look at higher. If I have time to follow up, so what would happen is that the yield stress that I define, the yield surface that I define, that's something that's a guess, that's an estimate from my model because it's a regularized model. So indeed, if you want to have a better estimate, you can go to different norms that I would say, and we can discuss it later on if the time is not there. Yes.
Thank you, Mr.
Can you be satisfied with this answer?
Very much. Thank you.
Very good. Thank you. Then I would like to ask Professor Rolfs to continue the opposition.
Thank you very much. Yeah, candidate, first of all, let me congratulate you to your really nice thesis and the nice numerical simulations you did. I was really astonished that you're able to make those energy balances. And there's not any numerical energy left that you cannot describe or that gives the maximum value that exceeds the 100%. So my first question goes to chapter number 4. You have the diagram or the regime map, and the regime map has on the one axis the Weber number and on the other one your parametric C. Why is there a limit of 1? What happens if you exceed this limit of 1?
You mean in chi, like
Sorry, yeah.
Basically, go for, because the chi is essentially the distance divided by 2 times r. So you would just go so far that the 2 drops will never see each other. Well, they will see each other when the impact happens and then the impacting drop spreads, and it might do something with this. But yeah, but that's, I mean, our reason was, okay, like if you had 2 solid balls falling down, then after G1, they would not interact. So let's say so to limit our study, we wanted to just look at 1, but of course you can go higher, and then while spreading, they might interact as well, yes.
Okay, so the reason for limiting your case there was to say, okay, it could, if you have these stable balls, then that will happen.
Yeah, it will just touch, graze each.
Yeah. Okay, that's good, very nice. The next question is, you do a lot of analysis in terms of energy, but have you also looked at the integral momentum of each drops? Because you come to the conclusion that if the drops are bouncing from the wall, they go into different directions. Wouldn't that be a simple explanation based on momentum of the drops and the force balances?
Indeed, that's true. So essentially, if you look at, so what we did do there was we looked at the velocity vectors. So if you look at 4.4.1, so all the like arguments that we made regarding that motion and so on was all based on this velocity vectors that we get in numerics, but not in experiments. But at that time, our main idea was, can we explain the experimentally observed situations? And there we chose to stay with this velocity vectors and not do an integral of momentum. Probably it would be an integral of like a total momentum of the drop, and that would indeed give us a more realistic direction of motion of the droplets. But that was just
that's nice. It was very good. Well done. The last part of my questions will go to chapter 6. And I was able to observe your phenomenon in swimming in a lake. So I saw little drops jumping off, and then I also saw your phenomenon while cooking, because if you cook like tomato sauce, you will see those films first. But now what I see is there's a cap of a film actually on top of the liquid, and not like the liquid that bubbles that bursts before creating the cap. What was your reason to omit this cap, and would it make a big difference if you account for the cap?
So the short answer would be that for low bond number, it will not have an effect, because for low bond number, that cap itself is quite tiny, which was the topic of this thesis. However, if you go to high bond numbers, then indeed you will have a bigger cap. For example, soap bubbles are known to create huge caps, and then when the bursting happens, it will be the droplets that you get will be from that cap. In fact, when you look into the literature, you would see that the bubbles, the droplets that you see while swimming and so on, there are two origins of those bubbles. One is from the cap itself when it breaks, and second is from the cavity which collapses and then leads to droplets. So, but we just the reason we remove it, because we were in the limit of 0 bond, and we could we didn't have to worry about those caps, because they're just so tiny.
Okay, and if you would now try to make an experiment to validate or verify your numerical simulations, how could the experiment look like?
So I can answer that quite nicely, because one of the committee members is trying to verify that particular problem experimentally. So how he does it is, you create a bubble inside like a carbopole, for example, and then you would remove the pressure from the surroundings. You would use a vacuum pump or something, and you would essentially decrease this ambient pressure, which would mean that the bubble will grow, and as it grows, it will also rise up. And then when it comes to the surface, hopefully we will know, first of all, we need to know the initial shape of the drop of the bubble, because I assume it to be spherical or in a 0 bond limit, but that will not be the case. So we need to take that shape into account while doing future numerical simulations. But indeed, there is someone trying to work with this particular apparatus, which I just explained to you. And
okay, and then in collaboration with you, you're optimizing your numerical simulations to meet then the experimental conditions. That's good, I think.
Yes, that's because this was one of the first, let's say, explorations in this direction, and we do hope to follow up on it.
Sounds very good. Yeah, thank you very much. I'm satisfied.
Thank you.
Thank you very much. May I ask Professor van der Linden to continue the opposition?
Thank you, Mr. Chairman. Dear candidates, first of all, let me also congratulate you on a very impressive thesis. It was a pleasure to read. And it clearly shows that you do not only enjoy doing the research, but also make an effort and enjoy presenting your results in a very attractive way. And that also makes it, the reading, really a pleasure. So especially the regime maps that you create for each chapter, they give a very nice overview of the whole of your work. And I also would like to start my questions with one of these regime maps, namely the one of chapter 2 on page 60, where you look at bouncing and non-bouncing drops. So in your presentation, so in the introductions, you also make an effort to connect to applications, and you mentioned several in this case, where either the bouncing is wanted or unwanted. So I want to ask you if you can, for some typical examples, explain where they would appear in your diagram. And yeah, so what you could also do to optimize for the either the wanted or the unwanted effect, maybe more the wanted, since it's an unusual phenomenon in practice.
Okay, dear highly learned opponent, thanks a lot for your question and your kind words on my thesis. So indeed, well, I would first take the example of inkjet printing, because that's something that we both share in common. So if you go to, let's say, that Weber number, because there is also Weber number, which is a third parameter in this regime, but it turns out that everything collapses, and we have a reason why it does. So let's take Weber 50, which is a typical, well, 50 or even 100. Order 100 is a typical drop impact in an inkjet printer, and you would see, and you would want your drop not to bounce off from your substrate, because you need to print them on a paper or some. Although what I should mention there is that since the paper is not a hydrophobic surface, so it will probably never bounce off. But then that would be one, let's say, example. Another would be, let's say, pesticides, which you won't want to bounce off. However, if you look at, let's say, nature, for example, in a lotus leaf would want to keep itself dry, and it would like to bounce off the water droplets. And if it's a 1 millimetric water droplet, like rain, well, I don't know exactly the radius of rain water droplets right now, but let's say if it is 1 millimeter, then that would be Ohnesorg of 10 power minus 3, and that would lie in the left part of this. So if, as long as the size of the bond number is less than 1, you would still bounce off. But if you have a higher bond number, which would mean that the drops are bigger, but that would also change the Ohnesorg numbers to even smaller values. But then they will not bounce off from the lotus.
So the parameters you recommend to change, if you can, would mainly be the size of the drops.
That's how I think about these two numbers, because I think of a bond number as essentially the ratio between the radius or the length scale of the droplet to the gravito-capillary length scale, and I think of Ohnesorg number as the radius to the the inertia visco the visco-capillary length scale in that case. The one which controls the dissipation.
Okay.
Yeah.
So let me continue with some other data points in this figure. So you compare to experimental data. They very nicely coincide with your numerical work.
Yeah.
I noticed that there are no data points for low bond order number. So I'm wondering if you can say something about what kind of experiments you would need there, and if that's even feasible to do in practice.
So in my layman talk, I show one, let's say, a video, which I always show, which is Scott Kelly playing ping pong with water droplets in space, where the effective G is 0, because it's you're in a free fall situation there, and that would be the data point. But I will probably have to ask him what was the Ohnesorg number where he stopped bouncing, because he only played it with water droplets. So I did not plot it here, but that would be, well, of course, we cannot all go to space, but we could go to like a free fall tower, and if you could make a setup that would still be able to sustain while it is freely falling, then maybe we can get more data points there.
Okay.
So probably a challenge for experimentalists.
Yes, absolutely. So you mentioned also the idealizations that you use in your numerical work. So what if you were if those idealizations are not in place, how would you expect this regime map to change? Can you say something about that?
Yeah, well, there are several idealizations, so maybe if you have any one particular in mind, so I start with that, or I can just give you a general overview.
Yeah, so I think you mentioned the substrate and the effect of the surrounding
indeed.
medium.
So, so there is recent work on this topic, which is somewhere in the references, where they do it on a super. They say it's a superhydrophobic substrate, but I could see from their movies that the drop pins on the substrate, so there's a pinning effect is there. And then what we see is what they see is that the inhibition of bouncing happens at Ohnesorg less than 1. In fact, I think one of my paranims also did similar experiments for Canon, the inkjet printing company, and there also he used droplets which stopped bouncing at Ohnesorg 0.25, 0.3 in that range, and not really at 1, or what would this predict. But that's because the substrate, they still offered some pinning effects. And you could even see at times that a small part of the droplet would stay in the substrate and the rest would pinch off and go off as well. So those will definitely influence the process. But what we wanted to do in this work is to say, okay, if everything is ideal, then even in that case, you would not always keep on bouncing. So as Professor Kare mentioned, as the first highly learned opponent mentioned, that bouncing is more exotic and we want to understand it more. But then it's not something that will all keep on happening if you change the parameter. So that was the main idea, to give a upper bound to this this process of bouncing to non-bouncing.
Yeah, so in practice, there is, of course, as you well know, in applications, you don't deal with ideal liquids normally. Yes. So there's all kinds of things in there, like particles, surfactants, salts, usually in combination.
Yes.
So how would you deal with such a situation if you want to know more about what will happen?
So one of the biggest issues with that is the characterization of the liquids. And as you know that, for example, in these chapters, I use the Newton's viscosity versus like stress, viscous stress versus strain rate relation, which is a linear relation. But of course, once you start adding things to the droplet, that will change. And as long as I know the rheological properties well, and it's properly characterized, ideally it is possible to implement those in as well. And in fact, there are follow-ups to this chapter where we are working with the inkjet printing company Canon to look into those effects. Because indeed, ink, for example, is not Newtonian.
Okay.
So it has all kinds of stuff in it. So. Yeah.
So
but we do need a good characterization of the rheological properties before I could put them in the numerical model.
Yes,
of course.
But if you would have those, if you characterize the rheological properties fully, then you say you can also predict what will happen.
Yes, I don't see a reason why not. But of course, when actually writing the code and actually implementing those, there might be some hurdles in the way. But yeah, I think we can figure those out. Yes, as they come.
So that brings me to a nice question to finish my opposition with, namely, let's say if you can spend 6 more months on this research, so what topic would you choose and what would you do? What would be your priority?
Well, first priority would be actually the one that you just mentioned, that to use like something like a viscoplastic liquid instead of a Newtonian liquid and look at when that stops bouncing. But even before that, because what is important for, let's say, like inkjet printings is not like bouncing or not, because we know it will not bounce, but rather the maximum spreading radius of the bounce. And as probably some of the committee members know, that it's a hot debate as to how is the maximum spreading diameter related to the impact parameter itself. So even for Newtonian liquids, there is no definite consensus about it, but indeed adding, let's say, viscoplasticity would make it even interesting. Another, let's say, direction that I would like to go is something that the second opponent works on, which is viscoelasticity. So working with something like an elastoviscoplastic liquid, because those really interest me a lot, because those are something where you could see many new features and new things. For example, one of my paronyms has seen in drop impact with a viscoelastic liquid, you could see Worthington jet, and then you could see beads on a string on a Worthington jet. So those really interest me a lot. So I know these are not easy simulations, as I think I know that, but I would try to make these efforts in the near future. Also, for chapter 1, well, we restricted. That's one of the only chapters where we don't vary the Ohnesorg number. And as you can see, the title of the thesis is Viscous Free Surface Flows. So you would expect that I like Ohnesorg numbers a lot. So chapter 1 needs like a thorough investigation of varying Ohnesorg number and see how the peaks change when we vary Ohnesorg number.
Okay.
Yeah.
So since I seem to have some time left, I will continue, if I may. Yeah.
Yes,
okay.
please go ahead.
So I think you mentioned in the outlook of chapter 2 that it would be interesting to also investigate whether you see this whether this criterion that you use for the bouncing to non-bouncing transition also works for coalescence-induced bouncing.
Yes.
So what is your expectation of that? Do you have any idea up front what?
So I will have to give you a brief history why I think why I want to do that is because on page 63, when you look at the arguments that led to that very simple Ohnesorg plus bond equals to 1 equation, we use a lot of information from the coalescence-induced jumping of droplets, which is one of the which is in fact 3 papers, 2 of which were done by the first opponent in this committee, and we use those results to investigate our drop impact process. So what I hope is to get the same result when I go back and do it there. Yeah.
Thank you very much.
Thank you, Mr. Beadle. Can I ask the candidate and his paronyms to retake their seats in the audience? I adjourn this public meeting of the Doctorate Board of the University of Twente. Ladies and gentlemen, I reopen this public meeting of the Doctorate Board of the University of Twente. Can I ask the candidate and his paronyms to stand before this table? The Doctorate Board of the University of Twente, represented by us, has examined your dissertation and the statements accompanying it, and heard your defense. The Committee of Deans has decided, in accordance with Article 7.18 of the Law on Higher Education and Scientific Research, to admit you to the degree of doctor. I request the first supervisor to carry out the appointed task. Please rise.
Did you turn? Yes. Under the authority assigned to us by law and on behalf of the Doctorate Board, I grant you, Vatsal Sanjay, the degree of doctor and all the rights that are attached to this degree. As evidence of this, I present to you this diploma, signed by the Rector Magnificus, the Secretary of the Graduation Committee, and your supervisor, validated with the seals of the University of Twente. I'm pleased to announce that the Graduation Committee has decided to grant you a doctorate cum laude with distinction.
Dear learned Dr. Sanjay, let me congratulate you also on behalf of the university on your acquired dignity. From now on, you have the right to use the title of doctor. This title implies that society can rely on the quality of your judgment. and that you will act with integrity and transparency, and that you will communicate independently about the results and the social relevance of your work. Value the doctoralis as an honorable distinction and a well-deserved prerogative, but always remember the obligations imposed by it towards the scientific community and society. Congratulations. May I ask the the laudatio. Okay, sorry. So I would like to ask the promoter to pronounce the laudatio. Please sit down.
Dear Vatsal, dear Dr. Sanjay, congratulations on achieving the doctoral degree, cum laude distinction. It's a very special performance. It is highly deserved. We have seen this just again in your great defense. We first met about four and a half years ago by email and then by Skype. Zoom was not so known in the pre-corona times. Your application to a numerical PhD position of my ERC advanced grant on diffusion droplet dynamics was extremely strong, and it was a no-brainer to make you an offer. In fact, we were very happy that you took this offer, as you had competing offers from good American and British groups. Already then, you were an expert on the volume of fluid code basilisk from your prior work as master student. Now, after 4 years of PhD, you are one of the world's masters of the volume of fluid method and the basilisk code. You extended it in various directions and applied it to various flow geometries and situations. But most importantly, for all these cases, you have wonderfully worked out the physics of these flows. The common theme of the thesis are drop impact situations or retraction and bursting situations where viscous forces become relevant. Of course, as base case, the low Ohnesorge case had also to be studied. And Ohnesorge number, as stressed again, is clearly your most favorite dimensionless number in fluid dynamics. Most chapters culminate in the parameter spaces. The huge amount of through-cuts of the parameter space you analyzed becomes particularly evident in your conclusion section. Another common thread of your thesis is that the numerical simulations are compared with experimental data. The quality of both is always so good that a one-to-one comparison has been possible, and this is something which clearly, say, 15 years had absolutely not been thinkable of. A particular nice example for this sort of comparison is chapter 1, where you study drop impact on a superhydrophobic surface. The key finding is that there's a second peak in the force which the impacting droplet exerts on the substrate, occurring when the drop takes off again. You have wonderfully worked out the physics of the flow leading to the second peak and provided great numerical simulations and perfect agreement with the experiments. The corresponding paper is presently under review at PL with 3 very enthusiastic referee reports in the first round, which is something which is not seen so frequently. And I'm also glad that you wrote a shorter paper to PL, because I think it's also very good to learn how to write PLs. In chapter 2, you realized that next to the Ohnesorge and the Weber number, also the bond number is relevant to determine the outcome of the drop impact event, and beautifully worked out the phase space of when the drop bounces back and when it stays on the surface. Most remarkably, you found an excellent scaling argument to understand this numerical finding, which is in perfect agreement with the numerical data. In chapter 3, you studied droplet impact on thin films. You looked into the local energy dissipation rate diagram here in the Ohnesorge versus aspect ratio parameter space, identifying the floating regime, the substrate-dependent bouncing regime, and the substrate-independent bouncing regime. In chapter 4, you studied the impact of one drop on another one. Also here, the various outcome scenarios can well be understood with energy arguments, and the phase space has again very nicely been worked out, giving very good agreement between experiment and numerics. This paper, in fact, historically was your first one, emerging out of a collaboration with the Max Planck Center, Gross Former, and at Mainz. And you learned tremendously here on paper writing and on working out physics. I think that paper and work was an excellent practice for you in many ways. Chapter 5 is the longest chapter, corresponding to 38 JFM pages, and it would have been even longer if I hadn't prevented this further growth. But you beautifully extended the Taylor-Kulik retraction of a droplet in air towards the droplet retraction in another host liquid, and to the mixed case of air from the top and other liquid from the bottom. It was your original idea to proceed along that line, and you found new scaling laws and rationalized them in a great way, again, employing energy arguments. Also, this chapter culminates in a phase space, showing the different flow scenarios. Chapter 6 deals with bursting bubbles in a viscoplastic medium, again, combining experiments in physics and simulations. To my knowledge, this is the first basilisk calculation for a non-Newtonian liquid enabled by your extension of the code to this non-trivial flow rheology. The mileage, Vatsal, you have made in your thesis is really major and breathtaking. The work also opens many new doors and perspectives. The thesis is a true masterpiece, full of ideas, creativity, written with utmost care, and a tremendous pleasure to read, which all members of the committee have emphasized. For this great work, you also had great collaborators. It is also necessary for the experiments, as you have up to now not been known as a world-famous experimenter. This, of course, can still change. But for those who do not know, Vatsal did help with experiments in the lab, and of course, he is a great source of inspiration. I cannot name all your co-workers here. They are the co-authors of the papers, but I would like to mention some of the POF colleagues with whom you intensively interacted, namely with Marzi, with Udo, with Pierre, with Srinas, and with Yusuf. And thanks to all. I think I can speak for all of them and express what I have experienced over the last 4 years. It is a great pleasure to collaborate with you. Adding to all what I mentioned before, what makes it great to work with you is that you are science-driven, interested in the physics of the phenomena and to understand things. This also implies that you are very generous with your ideas and also with your time and also with the order of authorships. Your generosity and curiosity, your depth of understanding, your care and your critical mind make you the ideal referee for journals. And I must admit that various JFM editors made massively use of this, and I'm sure that Physical Review Fluids does the same, and we have one of the editors of Physical Review Fluids here. I cannot check for Physical Review Fluids, but I checked yesterday for JFM. You have written 31 JFM referee reports in the last 4 years. Your average turnaround time is 19 days and 6 hours, and you have written 10 reports in the last 12 months alone. The last report you delivered 2 days ago. And in particular, these reports are all first class and very helpful for both the editor and for the authors. I'm not aware of any other PhD student on a world scale who achieved these numbers. Other examples of your generosity are that you were an excellent teaching assistant for 3 years in advanced fluid mechanics, that you helped me preparing my online lectures, and finally, very recently, you taught me how to Twitter. I don't know what the world will have out of this, but you taught this to me. So you helped the community and the group in many ways. In a nutshell, you contribute to create the great intellectual and friendly climate we have at our POF group. So all of us are extremely happy that you will stay on here as postdoc. You and we have lots of projects in our mind, and some were discussed in the defense, and I'm very much looking forward to further collaborating with you. Let me extend the congratulations to your wife, Anjali. I'm glad that you could finally come, and I am wishing you all the best and that your plans will soon become true, which the plans which you have in mind and which we, well, with Vatsal and I and you, we all discussed. Finally, I would like to thank all committee members for their contributions. David, for the good interaction we have had over the years. It's always a great pleasure, and it's a pity that we cannot be here in person. I hope at some other location and occasion. So it's postponed, but well, hopefully it will happen soon. I hope that Vatsal's thesis convinced you or further convinced you that numerics can be great and very useful. Then I would like to thank Wilco for good discussions and surely many more to come, also jointly with Vatsal. Also there we have concrete plans. Then I also would like to thank Mazi for a great collaboration and also more to come. You have played a great role in Vatsal's thesis and time here, and I really appreciate this. And of course, I would like to also thank our FIP, Fundamentals and Inkjet Printing colleagues, Harold and Marlene. Also, there are many more work to be done jointly and also with Vatsal, so this will also be great. And of course, I would like to thank our chairman, Devaraj. Thanks, Devaraj, for doing a great job and filling in 2 roles today. And I would like to end with wishing Vatsal success. Vatsal, het ga je goed en succes.
So now let me congratulate you also on behalf of the faculty at the University of Twente. It's great to have you as a new doctor in this, and of course with distinction is really very special also to the university and the faculty. And there was very little I need to add to Detlef's laudatio, which was beautiful. The only thing is that you even did more than is just in this thesis, and that is work that is still in progress and things that may at some day bloom as well. But and the thesis is already such a magnificent and huge piece of work. So thank you. May I ask you to retake your seats in the audience?
Can I say a few words to the committee members?
Yes, one more, just afterwards. So I just want to say a few words about how we are going to leave this room. So first, the beadle will leave the room, then the candidate, his parents, and his family, his wife, and afterwards the committee members, and then all the other members of the audience. And before we do so, there is still the possibility for the candidates to say a few words to the committee members that have joined online. But with this, I close this public meeting of the Doctorate Board of the University of Twente.
Thanks a lot for being in the committee, Professor Kare. I have admired your work a lot, and as you can see, 5 of the 6 chapters are inspired from your previous work. So I hope that you enjoyed reading them, and I hope to also talk with you in future and collaborate on more things. Professor Rops, first of all, I'm really sorry that I did not address you properly during the defense. I'm really sorry about that. But we also have concrete plans to collaborate, and really thanks a lot for reading the thesis. And Detlef, Professor Loze, I'm really glad that with the speech that you made, it will take me some time to sink that in. Thanks a lot for giving me the chance to work here. I mean, it has been amazing, and I look forward to working with you closely and learning a lot many things from you in the future. And hope to see you soon. Have a speedy recovery.
Have a nice day. Yeah, enjoy your day.
Vatsal, and have a nice party this evening. Unfortunately, as you know, I cannot come, but I'm sure you will have a nice party anyhow.
Thanks. I hope we do it soon.
Good.
Thank you.